Hello, today we're going to be starting our first of two chapters on how to describe and display data. So specifically, we're going to look at our first type of the two major divisions for variables. So we're going to be looking at categorical. And then in our next chapter, we'll be doing quantitative. So since there's two major types, we split them into two chapters, and we're going to be looking at both those characteristics for it. So we're going to look at how can I display this in a meaningful manner, aka can I make a picture that tells me what the data is doing? And then we're going to talk about how can I describe it. So describing is going to be a couple different things. It's a matter of also not only describing the image that you get off of the graph, but it can also be things like numerical values, like, oh, what's the average, what's the typical value? So typical value is going to be one we talk about a lot. So when you think typical, I want you to be thinking, like if your boss came up to you and said, hey, what's the price we usually pay for this product that we need? Something like that. A reasonable response to what the average or typical value is going to be. All right, let's get into categorical. So the first thing we're going to talk about is how to summarize and or arrange categorical data in meaningful ways. There are going to be two major ways we do this. The first is what's called a frequency table. This just organizes the data according to how often it occurs or how frequent it is, hence the name. So the way we do this is usually using a simple table that reports the counts or some other way in which to organize or say how many of those specific categories occurred for the categorical variable. So here's an example for you. The Super Bowl. So one of the more interesting polls the National Football League of the United States did recently is they took a bunch of viewers and they asked them, hey, you know, why were you watching the Super Bowl? So some people will say, I was watching for the commercials, or they don't watch the game, or they watch the game and they're more interested in the game. So if you look below, here's 40 respondents from the poll, and you know, this is very typical of how you get raw data. It's not organized in any way, shape, or form. What we want to do is we want to take this and say, well, oh, was it true that, you know, most people were watching for the commercials? Does that seem to be the case? How can we organize this in a way to where we can see, is there a certain group that's more prevalent than the others? And then we can form a frequency table. So you'll notice that I have a couple different things going on with this table. I have the response, which is, you know, what the people individually said they were responding to. And then I have it organized in two ways. The first one being the count. So this is called a frequency table itself, just the counts part. So just this portion of the table. And then next to it, I have the percentages. So the percentages here were found by taking how frequently something happened, the counts, and comparing it to the total. Count to total, and then changing it to a percentage. When we do this, this is actually called a relative frequency table. So if I would have just had the percentage part along with which response it went to, so these two parts together, ignoring the counts, that would have been a relative frequency table. Now, it's called relative because you're comparing your counts, your frequency, with a total. And there are lots of ways to build a relative frequency table. We're going to see lots of them as we go through today's lesson. So when we're organizing data and creating pictures to represent what's going on with the data, there are three things that you should pay attention to. We do pictures for a reason. We want them to reveal something about the data that we couldn't see by just looking at it in raw format. We want these to show important patterns or features that might not be noticeable if we didn't organize them. And last but not leastly, we want to find something that actually helps us report what's going on. And I really want to add a fourth one to this. This is the three displayed by the book, but you should also be aware of, you shouldn't be making it look like something else is happening. You know what I mean? No deception. Be real. So here's an example that sort of violates that idea. So I want you to compare two things. Look at direct, compare it to Google. If you looked at these two images, you might say to yourself, oh, how much bigger is direct than Google? And in order to do this correctly, you should be looking at how long they are only, but these are using area. This is called the area principle, as the title suggests. And you might look at direct compared to Google and be like, oh, well, I could fit like, you know, I got a shoe this size, I could fit like one there and one there and one there and one there, about 4 times, maybe 3.5, because this one doesn't quite look right, you know. So Google looks to be 4.5 times the size of direct, but that's not true. If you compare these two, When you're looking at 23% versus 57%, it's only about twice as much. So the problem with the area principle is if we look at area, we're looking at 2 dimensions. But in reality, the only thing this was scaled by was 1 dimension, length. See, about twice as much in red. So we don't use area. These are called pictograms, and they're problematic for that reason, because they are using area, which is 2-dimensional, to represent a 1-dimensional relationship. Don't use area. Although they're fancy looking, they're distracting and usually lead to misconceptions about the data. Shoes are fun, right? Anyway, so the best displays that observe the area principle, area magnitude, and multiplied by the graph should respond to the magnitude of the value that occurs. That's fine. So if I would have made the shoe twice as big in area only, not in just 1 dimension, that would have been okay. But then it looks less dramatic. The other way that we can organize categorical variables is using bar charts. I'm hoping one of the things that you'll see here is that the bars are organized according to the different categories within the categorical variable, and their height represents the frequency. This also could be done with using relative frequency. So there are 2 things that these charts are really doing for you. They're telling you what the values are and how often they occur. Oh, those arrows came out terrible this time. That's fun. So as you look at this, there's the 2 characteristics that a good chart will tell you. What were the values? How often? And it gives you a way to compare. You can be like, oh, well, you know, Facebook appears to be not doing as well as Direct or Google when it comes to our advertisements for this, you know, thing. And I know you might be tempted to make your charts really, really visually entertaining and really snappy and pretty and stuff. I'm more concerned with them being accurate than being fun, because accuracy is more important than being distracting. I sound like a nerd. Anyway, so this is the same chart. Notice it shows you the same kind of behaviors. Oh, clearly Google is the largest, with Direct being about half of that. But notice that this uses percentage, because this is a relative frequency bar chart rather than just a frequency bar chart. So in comparison to the total, this tells you what percentage of the market advertisements came from Google. Fun times. All right, so the other way you could organize this data for Keen Ink, which is the shoe company's data that I've been using this whole time. I should have mentioned that earlier. Too late now. All right, is pie charts. So here's the same idea using pie charts. Or sorry, same data using pie charts. I'm not gonna lie to you, I hate pie charts. I think they're incredibly confusing. There's some things about them that are very, very negative, I think. No matter what you do, you almost always need an other category. As you look at the pie chart I have in front of you, the only thing you can really say to me is that Google appears to be the biggest and more than 50%. And then the rest of these you should look at and be like, I have no idea what their percentages are because it's completely unlabeled. When you go through the mini-tab videos on how to create pie charts, I actually show you how to make a better version of this. So it actually says like, oh, what percentage is this? So it's like 53 something. And it displays the values so that you have some idea how large they are. Otherwise you're left to guessing, which is, you know, the only thing that really gives you is comparison. The other thing is that pie charts can be incredibly deceptive because they are area, and most people have a difficult time reading that correctly. Yeah, so other category, make sure you label things and then you don't have such a bad time. Usually the other category is just made up to make it so that your chart adds up to 100%. One of the more frequent things I see happen is people will end up with a pie chart with stuff under 100% because of rounding, and then they just add another category for no reason to make it add up to 100, which is super, super bad deceptive math. Don't do that. The last thing you should notice is that when it comes to categorical variables, since this is our last one, I want you to notice that they all have the name chart. So if you're not sure what you're looking at and what type of data it is, if it says chart, it's categorical. They both start with C. That's fairly easy to remember. If it says graph or anything else, you should be thinking, oh, well, that's not categorical. Categorical variables are represented with charts. C for CEO. All right. So before making a pie or bar chart, hey, did you know you need to have categorical data? This is like just what I just said. That's kind of embarrassing. This is stating to you that, oh my gosh, this is the type of data that these types of displays go with and nothing else. And make sure your categories don't overlap. If you have overlap, you actually can't do just a single bar chart or single pie chart. You need more complicated ones. We're going to do some of those today, so it's all right. And the other thing to be careful about is be careful about what you're trying to communicate. If all you're trying to communicate is comparison, then a pie chart works fine. You can look at these two and say, oh, cool, that one's bigger. If you're looking for more detail, I would suggest using the bar chart. All right, so how can we explore displaying two variables? Woohoo! I said that was coming and it was suggestively soon. So if we want to create and look at the relationship between two different categorical variables, we're going to use things that are called contingency tables. Now there are types of bar charts and pie charts that you can do with these. The bars are a little bit easier than the pies. But first we're going to go into how can I organize this into a table, how can I use that table, and then I'm going to do the charts. All right, so when you're looking at contingency tables, this is the kind of information we're going to be looking at. We're going to be looking at what are called marginal distributions, and these are a way to look at the variables as if one of them was not present in the interaction. We also can look at individual cells to understand what's going on between the two values. And then rather than displaying just counts, we also can do percentages in three different ways, since there will be variables going down columns and going across rows, as well as the total. You could do three different types of percentages. You could go across the row variable, you could go down the column variables, or you could use the total to do all of your percentages. So there's lots of different ways you can do your relative frequency now, and that makes this a little bit more interesting, I'd say, depending on what you're trying to compare. So here's a pie chart using some Pew Research data. If you've never been to Pew's website, they have lots of really interesting data on lots of different topics, so many different ones, most of them having to do with social interactions and things like that. But here's some ones on social networking. Woohoo! So this is a survey they did across a bunch of different countries where they asked the citizens, do you use social networking or do you not? And they came up with three responses: not applicable, yes or no. I was kind of surprised that there were so many people that didn't care. But I believe this was from 2013, so the data is a little old. So I'm sure that these numbers have changed if you look at this historically compared to now. So if you're looking at yes and thinking that's way too low, I totally agree with you. Here's how it looks if you look across the different countries. So I took the data that we just had in the previous slide on the previous table and I separated out across countries. So I'm hoping you notice that the totals that we saw in the previous slide show up right here on the last column total. So it's weird because now you have two totals, the total across columns and the totals going down rows. And this allows you to compare lots of different things. So if you wanted to know about how many British people said yes, you now have that information. It's right here. So when we look inside of the table and look at the values that are not on a total column, those represent two variable categories: the response, specifically yes, and the country, specifically Britain. So these are treated as ands. This is the number of people that said yes and are from Britain because they have both characteristics. Now you additionally can look at things like, oh, well, how many people were just from Britain? This is one variable value and it's down here on the bottom total. Woohoo! Or you could look at just the people that said yes, which would be over here on this total for the row variables. So this gets more complicated. And I could just look at, everybody, which is the total of totals, as I like to call it. That is not a technical term, just so you know as you go forward. So I look at all these totaling options. Earlier I told you, how do I find relative frequency? I take a value and I compare it to a total. Now there are three totals you could choose from. Yikes. Okay. What are we going to use this for? Well, we want to ask ourselves, do these countries behave differently? To actually answer that question, you need something from stats too. But we're just going to look at the percentages and say, does it appear that they look different? Does a certain one have more than others in certain groups? So looking down like the US's percentages, it appears most people said yes. And then the no's and the not applicables were like about the same. The only other group that kind of looks like that is, well, oh crap, most of them. I was going to say all of them, but then Egypt is like, nope. Anyway, and I would say the closest one in looking at this is probably either Germany or Britain, because they both kind of have similar values in the no and not applicable categories. Let's take a look at this. So the way we're going to investigate this is what's called a conditional distribution. This is looking across the specified values under the condition that you're looking at just one category. So either just yes, or just no, or just not applicable, and only its percentages, or just Britain, or just the US, or just Russia, or just Egypt. So, and ignoring the presence of the other categories within that categorical variable. So for example, if we want to know if these countries are similar or not, we can look at their conditional distributions. There are multiple of them in here. All right, so I want you to be looking at this and then asking yourself, well, how did I come up with these percentages? And this is also very typical of output. So I'm just going to draw this on the edge. So if you look at the first number, that's the count, and then below it is a percent. And then you got to ask yourself, well, where did this percent come from? Look down here at the bottom. Oh, these are all 100%. Aha, so it appears I'm doing my totals, well, not across, sorry, down the rows. So how am I calculating this? I'm using the row totals for all of the totals of, sorry, column totals for all of the rows that are in that column. So how am I coming up with 30% here? I'm doing 335 and dividing it by the total of 1018 and then converting it to a percentage. So same thing with yes, I'm taking 529 dividing by 1018. Da, 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 so on and so forth. So for instance, like the Russian value over here of 49.5 was found by taking 500 and dividing it by 1010 because that is the value that goes with that. So as you look at this, I'm giving the conditional distributions for the countries. So for instance, if I had just this distribution right here that I'm blocking off, that would be the conditional distribution for the US. Yep. And so you would write out just like, no, 29%, yes, 50%, not applicable, 21%, because I'm only looking at the US's totals. I'm not including anyone else's totals. You can also look at this and more clearly see who's behaving differently and similarly. Oh, only Egypt and Russia have low percentages for no, and then the rest of their percentages look pretty similar. So I would say those two look similar and are different from everybody else. Britain, Germany, and the US look similar to me. Again, I'm just saying that's how they look. This is not a formal piece of information. You know, to actually decide are they different, you would need what's called a chi-square test, which you will do in Stats 2 if you take Stats 2. Ta-da! Okay, so why would we look at conditional distributions? Well, we want to look for relationships, and specifically we want to see if these values are related. We want to know if they are what we call independent. Two things are independent is if knowing information about one, you don't really change your information about the other. Usually the example I give for independent is blood pressure. You look at the person sitting next to you, pretend there's somebody there if you're alone, and they tell you their blood pressure. That doesn't change your blood pressure. So knowing someone else's score doesn't change your score. That's clearly independent of each other. Dependent would be things like, you know, knowing a certain percentage of your class is left-handed, and then you get information like, oh, I know this many people are left-handed. You must know now how many are left that should be left-handed. There's too many lefts in that sentence. Anyway, we want to know, are they associated? Are they related? And usually the easiest way to do that is independence. We're going to talk more about independence when we hit chapter 5 and talk about probability and have a really good formal definition of it from there. So let's look at the Super Bowl example again. So I've made this into a much more complicated contingency table or two-way table because it has two variables now. I've taken how people respond to why do you watch the Super Bowl and separated it by gender. Because you may think about people like your grandma who's like, I'm not watching that stuff, or I find the commercials funny, so I'm going to watch it anyway. Anyway, we want to ask ourselves, does it appear there's some sort of association between gender and whether or not, you know, and how people watch the Super Bowl, or are these numbers pretty similar? I don't know. Let's take a look. So we're going to take this, we're going to change it into a more detailed table. So here is the conditional distribution for each gender. So I'm only looking down the men column, only looking down the women column. So notice the totals I'm using is by gender, and that's how I know these are the conditional distributions for gender. You could do just the men if you wanted to. So like the conditional distribution for men would be just this part. Anyway, so as you look at this, look at your percentages, compare them. Are they different? Well, the only one that's kind of similar is the people that don't watch it at all, right? These two. The rest of them look very different. So I would say that, yeah, I have enough information to say these are probably different from each other and therefore aren't associated. I just said that wrong. Therefore, gender seems to have an effect. For instance, if you know the individual you're looking at is a woman, they're less likely to be watching the game for the game. They're more likely to be watching it for the commercial or not watching it at all. There you go. So it appears that knowing gender has an effect. Therefore, gender is not independent of Super Bowl watching behavior. Alrighty. Here is an example of how you can display two categorical variables against each other. So this is what we call a side-by-side bar chart. This is specifically a type of this is a specific type of what's called a segmented bar chart. There's another segmented one we're going to do in a minute. So it just sits these two next to each other according to the different categories of response. Oh, I'm sorry. And then it color codes them and sits them next to each other based on gender. So I'm hoping you notice that. And that's just a simple way to do that. But notice that this has to be a contingency table. It can't be just counts. You have to be separating somehow. You can't have just one bar. Well, unless you separate that bar into pieces, which is what we're going to see. So the other one we're going to look at is what's called a mosaic plot. So mosaic plots are a little bit more difficult to read. They take the whole bar and segment it and divide it into parts based on the percentage for that group that represent both categories. And this is a little bit more difficult to read. Here's a little bit of what they look like. So to make our mosaic or segmented bar charts, we're going to look at some new data from the Titanic. So in case you didn't know, the Titanic was a ship that was thought to be unsinkable and then sank in April of 1912. It's also a really weird movie. Anyway, so what we have below is the passengers that died on the Titanic and the ones that lived, separated by where their cabin was located. So if you've never been on a ship, the class of cabin determines location. So first class usually can see the light outside their windows. Second or third class, depending on the height of the boat in the water, is usually either underwater or able to see the sun. And then crew is usually like where the crew is housed, which is the bottom bowels of the ship, wherever they can fit it. So one of the interesting things to look at here is based on where people were located, were they able to make it out alive because they were able to get to the little boats that they have on the boat to save people? What are those called? Lifeboats! Yay! Anyway, so looking below, you'll notice that I have the counts and the counts by column, and they're done by columns so that we can see the effect of class on whether or not someone lived or died. So in looking at first class, about 62.5% of people, when compared to only other first class passengers, survived. That drops to 41.4%. When we look at second class, third class is down to 25.2%. And then crew is down to 24%. We have lots of data on death. Statistics can be a little depressing for that reason, but I'm hoping you notice that this is a huge reduction. So it appears that when you look at class as compared to survival rate, there is an effect based on where someone was located at in the ship. Let's look at that as a plot. So here is a side-by-side chart. So I'm hoping you notice the alive amount as I increase my likelihood of being in the bowels of the ship, aka going this way, seems to be going down, and my amount of purple bar, or aka the percentage of dead, goes up. All right, well, this is kind of depressing. Anyway, so survival! Yay! Boats and stuff. Know how to swim. So here's a mosaic plot of that same data. So here we have the segments separated by class and the bars created by whether or not the individual lived or died. So one of the nice things about mosaic plots is it makes you more easily able to compare certain groups. So as you can see, the alive category appears to be pretty spread out, but the dead category is where you see a definite difference. It appears that a far greater number of third and crew individuals died, whereas these are almost similar in width, in percentage for alive based on crew. So one thing that allows you to say is that, oh yes, alive and dead are very different. So it appears that class did have an effect on whether or not somebody lived or died. Sad but true. So here is another mosaic plot of the same thing. This one is by percent as well. using alive or dead. And the spread of this kind of mosaic plot is very, very different because it's also based on size, not just percentage, and that it's representing for you the width of that. This is a very strange plot to read. I don't really like this version of the mosaic plot, even though it's pretty, but it's a little bit less informative. Anyway. All right. Simpson's paradox. So Simpson's paradox is basically the idea of, hey, if I make these percentages inappropriately, I can try to convince somebody that I'm right. How is this usually done? Well, it's usually done by combining certain groups or values. So you have to be careful about this because really the only way you should be combining percentages is if you know those groups are similar and or are independent. So you have to be kind of careful because if they're not independent, you might have some overlap or something in common. And then you wouldn't have accounted for that and it would have counted everybody. Let's take a look at this. Let's do an example. So here I'm looking at Peter and Katrina, and he's trying to argue that he's a better salesperson because they're selling printer paper and flash drives. And if you look at their totals as compared to, sorry. Oh. So take a moment and look at this table because Peter is going to be like, hey, well, I sold 83% of my offerings in the last 120 prospects, and you only did 78. But if you look at their individual offerings by product, well, with printer paper, yeah, Peter was very successful. With USB drives, he was not so successful. And Katrina was better in both groupings, but when you average across the totals, it doesn't look that way. And this is where you need to be careful, especially if certain groups are heavy-handed. So for instance, it's very significant that when you look at just paper, yes, you know, Peter did more sales on there. And when you look at Katrina, more of her sales are focused in USB drives. That difference appears to have an effect. So it really is the fact that Katrina is actually outperforming in both products, but when combined, the overall performance appears to not be that way. And this is because you need to ask yourself, is there another variable interacting and causing the difference? So just watch out for that. More detail is always better than less detail, and don't look at just totals or overall to try to decide whether or not something is happening. It's always the devil in the details. All right, let's do a really long, big example that goes over everything we've done today. Woohoo! Who's excited? Okay, so the following is a contingency table that shows students' major based on which state they arrived from. And we want to ascertain some information. We want to get some information from this, so we're going to come up with some marginal distributions. Then we're going to answer some questions about what type of students we have. Then we're going to look at a conditional distribution, and then we're going to construct some bar charts. I think I actually skipped these last two in this version of the notes, so I might not actually do the last ones. We'll rely on Minitab to do that for us. Anyway, so the first thing we're going to do is we're going to come up with a marginal distribution for home state. Marginal distributions have their name because they only use the margins, the totals, to come up with things. So when you're looking at a marginal distribution, you're going to ignore the other variable present. So I have two variables that are actually interacting here, home state and then major. Since I'm only looking at home state, I'm going to ignore the fact that major is here and look at only my totals for Pennsylvania, New Jersey, New York, and Maryland. Let's take a look at that. So what we first do is we create the total for each of the states, and then that's our distribution. So that's it right there. So if you were to write this out, what you should do is call it home state, write the state, PA. This is the most interesting thing I've done in a long time. This is totally not going to fit. And then you would write your total counts. So this is if you were doing a frequency table, not a relative frequency table. If I was doing relative frequency, I'd change these two percentages, but since I'm just doing counts, I'm just going to write out the counts. So you wouldn't even write like the rest of this. You would just write out the counts and ignore the fact that the rest of those occurred. So this is a way you can get a one variable piece of information off of a two variable table in case you don't need the other variable for whatever reason. Now let's do the marginal for major. So if we were looking at the marginal for major, we only need the totals for major. We don't care about what state they're from. So we're going to be adding up down the columns. So I would be looking at the totals for biology, accounting, history, and education. So I'd be using this as my table. So to write it out, you would write it out similar to what I just did. You'd write biology 270, accounting 210, history 205, and then education 215. So that's how you obtain marginals. They're literally on the margins, on the edges, using the totals on a table. Okay, the first thing we're going to look at is what is the percentage of students that are accounting majors and come from Pennsylvania. This is actually what we call a joint distribution, or a join, because it joins together two categories, accounting majors and from PA. So joins usually have the characteristic that their counts come from within the table, not the margins, and their total always comes from the total of totals, everybody who's present. So if you're looking for, is this a joint probability or a joint distribution, that's how you're going to find them. So since we have that looking at accounting and PA, Pennsylvania, I looked down the Pennsylvania row and noticed that 65 of those individuals are in accounting. That's how we get the numerator here. And then my total is out of the total of totals, which is the denominator. So I'm going to take 65 divided by 1,000 and get 0.65. So about 65%. I just realized that 65 out of 1,000 is, this decimal place should be over one more. This should be 0.065 and therefore 6.5%. That is an error. Oh well. Anyway, moving on. Next we're going to look at, hey, what percentage of New York students are education majors? So this is not a joint. This is, I'm only looking at New Yorkers and asking, hey, what are the education majors? So in a way, I'm basically ignoring the rest of the table and just looking at this value for home state. When you do that, you are forming a conditional distribution. This is called a conditional probability. So I'm only looking amongst this specific row because I'm looking under the condition that my student is from New York. So since that is the condition I'm using, the total I'm going to be using is 250 because that's the total for New York students. And out of those New York students, only 80 of them are in education. That's where the 80 is coming from. So be careful when you're looking at this, ask yourself, what am I totaling out of? Because that will affect how you're doing your calculations. Whew. Let's look at making a conditional distribution. Alrighty. So here we're going to find the conditional distribution for New Jersey. So it's very easy to do. We're just going to look down the row of just New Jersey. So I've removed everybody else from this table because we don't really need them. And then I just need to come up with the percentages for, well, just New Jersey. So I'm going to take 50 and divide it by 250 to get the one for biology. And it's essentially like ignoring the rest of the values for home state exists. So here's just New Jersey. So it's 20%, 16%, 26%, 38% for the following values of the major variable. So you list all of the other variable that's present and its percentages or its counts, depending on if you're doing frequency or relative frequency, for the condition of major is just New Jersey. Cool. Why would you bother doing this? Well, maybe you're wondering, hey, why is, what's going on with New Jersey? I don't get as many students from there. What kind of students am I getting from there? Should I put more of my efforts of recruiting into education since I get a lot of education students from New Jersey? Maybe. Depends on what you want for recruiting. This could be an indicator of something going on. Alrighty, that's the end of the big long example. Now I'm going to do something else. Okay, so here is an example from Excel of what you need to be careful about when you're making pie charts. This is what's called the 3D pie chart, and it's nice and flashy and everybody likes it for some reason that I'll never understand because I hate them. I'm biased. I'm aware of my bias though, so that helps. And you might look at this and be like, oh, shared is huge. It's like a big old slice of pie because it is the one facing closest to you, and this is in 3D, and you're violating the idea of, oh, I have something three-dimensional to represent a one-dimensional variable that has only these values. So it looks like the biggest piece, and it absolutely isn't. Actually, drive alone is the largest one, and I don't know why it arranges things like this, but it makes them automatically. Automatic is dangerous, just so you're aware. So the other thing to watch out for is, hey, keep it honest. If you look at this one below, 50% looks like it's smaller than half. That looks super wrong, and pie charts are weird for that reason and have so many places where people can make mistakes. And probably the reason this is occurring is that one or two of your rounding errors in here has created a missing piece and or an over piece because of rounding. Because if you add these up, it's more than 50. So that's weird. The other thing I would warn you about is if you find a weird graph, send it to me because I like weird graphs. That's not a warning. That's a, hey, help me out, because I think these are fun. Graphs. Alrighty. Keep scale consistent, because that can also be misleading. If you look down below, here I'm using a year scale and separating the bars in the same way, and here we're doing just months. Months are not the same as years. You know that. This can screw up everything. Alrighty. Be careful. Look out for different types of percentages. We now have row, column, and total totals on how we can do things. So ask yourself, which total am I using to make this percent? And be careful about it. And be careful about reading through a question when you should be using a specific type of total as you go through. Is it marginal? Is it conditional? Is it joint? All right. As always, make sure you know where your data came from. That's the lesson from chapter 1. Don't overstate your case. This is something that I think we could all do with a little bit of humility. So don't try to claim things about your data that it doesn't actually say, especially if you can't support it with either some sort of summary or graph. Alrighty, so what have we learned? Hey, we learned how to organize data. We did this in both one data piece and two datas. So we learned about frequency tables first. Remember, there are two types, frequency and relative frequency. And then we learned about how to chart that type of data, making either bar or pie charts to organize it visually. And then we learned about how to make contingency tables, which is how two categorical variables interact. This is kind of fun because it's our first time running across two variables. Our other time running across two variables will be in chapter 4. All right. Whew. When you're making marginal distribution plots, be careful about how you combine your variables and how you do that with conditionals as well. Don't try to state things that aren't there. Don't claim that this is all the data that you have because you've separated it out into pieces.